this next problem is going to be really similar. We've got a surf instructor who's trying to put a fence around an area. He's got some water here, a shoreline, and he wants to build the fence such that it forms a rectangle and is cut into two sections. Now, because of this shoreline, he doesn't need a fence there. So he's got this one section right here, which we'll call H. And he's got these three sections here, here, and here that we'll call X. A length of X for each one of those. We like to make any repeating lengths X. It just makes the problem a little bit easier. We want to minimize the amount of fencing needed. The amount of fence needed, which we'll call Y, is going to equal that length of X plus X plus X plus that length of H. In other words, we have Y equals 3X plus H. Now again, like the last problem, we have two variables, meaning we really have three variables, which is one too many. So we need to use a separate equation as well. Now the other piece of information given was that the area of this boundary needs to be 200 square yards. Whenever they're giving us what seems like too much information, it's actually going to be useful information for reducing our variables. We know that the area of a rectangle is equal to the base times the height. Now in this case of this rectangle, the base is X and the height is H. And we know the area is 200. So we have 200 equals the base X times the height H. And again, we're going to be able to divide by X this time to get H alone. So we have H equals 200X, which can then be plugged into the other equation. Now this equation could be Y equals 3X plus 200 over X. This is the fencing equation, which we'd like to minimize, so that will get typed into the calculator. Now I've typed this into the calculator, but I'm not seeing it, so I'm going to zoom out until I find it. There it is. This point right here is our minimum. It's the lowest point on that graph. Now I'm going to copy that vertex over, and now we're going to interpret it. This is the X, this is the Y. X represented the width of the fence that we need for the minimum amount of fencing, which would be 8.165 yards. And Y represents 48.99 yards, which is the minimum amount of fence required to accomplish the surfer's goal. This is what they were asking for when they asked us for the minimum amount of fencing necessary. Alright, this last problem might be the trickiest, but I think it's the most fun. So what we're doing is we're constructing a path to get from here to here. Now, it costs $10,000 per mile to construct this path over land, but it costs $25,000 per mile to construct it over water. Here is the water area separated by the shoreline. What we want to figure out is what is the best way to construct this path. So here's how it's going to work. We're going to take ourselves from here to some point on the shoreline, let's say here. We don't know exactly what this distance is. Now, what we do know is that this space from here to here is equal to, we'll call it X. And this space from here to here, well, if from here to here is 10 miles, this would be 10 minus X miles, because X miles were already accounted for here, so this is how much is left. Now that is going to be important. Now the rest of the way is from here to here. No, this is not necessarily a straight line. It may kind of look like it, but that's no guarantee here. Now what we have to figure out is, what is this distance and what is this distance? Well, these are both right triangles, which means we can actually use Pythagorean theorem to solve for this. Let's solve for this length using Pythagorean theorem. So we're going to take this side length 6 squared plus this side length x squared equals c squared. So we'll square root both sides, and we'll get that c equals the square root of 36 plus x squared. That's going to go right here. Now time to find this length. Again, we're going to use Pythagorean theorem. We're going to take this side length squared plus this side length squared, 10 minus x squared, equals c squared. We'll square root both sides, and we'll get c equals the square root of 4 plus 10 minus x squared. No need to simplify this. And this length goes right here. Now we're trying to minimize expenses. So our expenses, or our cost, is going to equal this length times how much it costs to build on land. So 10,000 times the square root of 36 plus x squared, plus the amount it costs to build on water, 25,000, times this length right here, creating a really messy but effective equation. Now back to Desmos with this equation. I'm using y equals, and you might need to be careful with parentheses. And now I've got that whole messy thing entered in, and I hit enter. And like the last problem, I'm going to have to go looking for this function. Now this one's a little tough to see, so I'm going to have to play around with the settings again. I'm going to set my minimum x to 0 again, and I'm also going to shrink the maximum x here because the graph was too skinny, so that means my window's too wide. So we're going to set this way smaller at 100 and see what that looks like. And there we go. Now we can see our vertex. And I'm going to copy that over and interpret it again. This x is going to be a little tricky to interpret. Given this picture, it means that we want to connect the path to the shoreline about 1.505 miles down. The y is a little bit more straightforward. It just communicates the minimum expense, that we're going to be stuck spending at least $83,676, and we'll round it to 87 cents. All right, congrats. You've made it through one of the tougher lessons in AMA. Just to recap, we want to start every problem with a picture. After that, you'll set up a formula for whatever you're minimizing or maximizing, and you want to make sure that formula only has one variable besides the actual variable of what you're minimizing or maximizing, the y. In some problems, we had to set up a second equation and use substitution to get down to this one variable. Once you get this equation down to where you want it, then you'll type it into a graphing calculator and get the vertex. Next, you have to make sure that you interpret this vertex correctly. The biggest thing to think about is what x actually meant in your original picture, and then the y usually represents the variable you were trying to minimize or maximize. If you had any other takeaways from this lesson, write that down now. Otherwise, we'll see you next project.